Let's say that you have an SD card and you have a library of movies in your standard hard drive. And you want to fill into the SD card as many movies as you can that would get you the largest watch time. So this is an optimization problem. And in optimization problems, there are a few basic techniques that are usually used, and I would like to describe these multiple techniques. Basically, we can look at the techniques, dividing them into two categories. One category is the brute force and its optimization, okay? And the other category is the greedy algorithm. Why did I divide it to these two categories? Because when I look at the brute force solution and its optimizations, and as we see, we can greatly optimize it, although it's not that intuitive, then these brute force and its optimization techniques would provide us with a correct solution. However, the greedy technique, which is the second category in this case, would not necessarily provide us with the correct solution. It could provide us with a good enough solution. It's pretty fast, but we cannot trust it to be a correct solution. In the brute force technique, we usually have a search tree. A search tree is where you have, it's like a decision tree, where in each step of the tree you decide if to take a movie or not. This is the brute force. We look at each movie and we ask ourselves, let's take a case where we take this movie, specific movie, and let's take another case where we don't take this specific movie, and now recursively solve for all the rest of the movies in these two cases. So while we could traverse all this search tree, we could stop somewhere. This is the first optimization. So we start with the brute force, we have search tree, we traverse all the search tree, which is basically the power set, all the combinations that we could have, and then our first optimization would be to stop at a specific node where we already see that we have utilized all the memory that existed in our SD card. While this is an optimization, this won't take us much far because we would still have many calculations, it would still be slow, and then there is another optimization. The next optimization is the dynamic programming. Dynamic programming would just mean if you made already a calculation, remember it, memorize it, put it in a dictionary so that the next time you need to do the same calculation, you already have the result in O1. So we started with the brute force. We built a search tree, which means the power set, check all the combinations, and then we optimized into backtracking, but this would be first order optimization and would not take us that far. And then we went to dynamic programming, which just means cache the results. This was the first category. And the second category was the greedy algorithms, where you say, okay, I'll just take the longest movie. I'll just sort the movies by some ordering. And in each iteration, I'll choose the longest one or with some other parameters, the best one for our solution. But as we said, the greedy algorithm would not necessarily provide us with the best solution. And why is that? It's because the greedy algorithm works under the assumption of a local optimization. It's fast, it's easy to implement, but local optimization means that if you optimize, in this case, for the longest movie, this means you might miss some other chances. For example, if you optimize to eat the most healthy food in your refrigerator, it might be pizza. So it's not the most healthy food in the whole of your possibilities. You could get some vegetables. This would be a global optimization. So if you locally optimize, you might miss some opportunities. And exactly this local optimization versus the global optimization is what means that greedy algorithm would not actually solve the problem. It could get us to a solution, but not necessarily. We cannot trust it. And then the problem with the brute force is that it's trying to check all the possibilities. And actually, if you think about it, then choosing the most helpful food would mean you actually need to traverse all the possibilities, or choosing the longest movies, you actually need to scan them all. There is no better solution. You must check all the possibilities. Who knows? Maybe there is a combination that you didn't check that would fit better with the length of the movies into your SD card. Which means that the brute force is the only solution, and we can only do optimizations on this. The thing is this, that with dynamic programming, with just caching, we can get into a much better state, but this does not mean that any problem that we could solve with brute force, with 2 to the power of n, with the power set, with checking all the combinations, not all problems can fit into dynamic programming, because we need to have 2 conditions on a problem in order for it to be applicable for dynamic programming or applicable for the memoization optimization. First, it needs to have what is called an optimal structure. An optimal structure means that you can solve the subproblems independently, and then you can combine them independently. Let's look at an example in our case. So in our case, we could look at subproblems independently. We could look at all the movies without the first movie and all the movies with the first movie and solve it independently, and then decide if we need the additional movie or not. Okay, it's all independent. This is what gives us the ability to split the tree, to do a brute force, and then to optimize. And then the additional, of course, condition is that some of these substructures should be overlapping so that we can cache it. Let's look at an example of problems which are not necessarily overlapping, so we cannot apply the memoization. If we look at the merge sort, for example, then obviously, if you take a look at the subproblems, if you split the array into 2, and you sort each of the subproblems, this does not mean, of course, that you would have the same substructures, same list of to sort. They are just random numbers. Of course, you could have, but it doesn't make sense that in most cases you would need to sort exactly the same items. So merge sort would not really be applicable for dynamic programming because its substructures are not following the second condition, which tells us that we could use dynamic programming, which is the overlapping structures. So to recap, the 2 conditions for being able to apply memoization, dynamic programming, caching is optimal substructures. The first one is optimal substructures, which means we can actually solve each of the sub-problem independently, as if it was a whole separate problem, not concerning our actual problem. And the second condition is that we would have overlapping substructures so that we can cache them actually. While in the previous optimization of the backtracking, we just said that we do not need to explore all the tree, all the combinations, because once we have a subtree, which is longer than the availability of the size of the movies that we can fit into the SD card. And no need to continue to explore this subtree. We can just backtrack. We can just say, okay, solution is not correct. Any movie that I add will not add anything. So this is the backtrack. So to recap, the set of problems that we have to explore, all the possibilities, is 2 to the power of n, because for each option we decide if to take it or not to take it. Then we have the 2 categories, the greedy algorithms, which would not necessarily give us the correct answer. However, they're easy to implement. They do local optimization, which is why they do not give us the actual answer. And they're fast. And then we have the brute force algorithms, where we build a search tree, where we ask for each item if to include or not include, which will give us 2 paths on the tree. One path to include, another path not to include. And from that, we move on to the next optimization, which is the backtracking, but it would not take us a long way. We just say, okay, this path on the tree is not good. I'm not going to continue to waste my time to explore it. And then the next big, huge step of optimization is the dynamic programming. For questions which answer both the optimal structure, we can solve sub-problem independently and have also overlapping substructure, which means I can cache. I'm really going to reuse this answer. This is going to give us the real boost. This is going to, in this set of problems where we can apply both these rules, this dynamic programming, this caching, this memorization is what is going to give us the real boost into optimizing problems which seemingly appear to be impossible to solve in this way, to the power of n, explore the combinations. So I think this was very interesting, and see you next time.